And lastly, we will have our undergraduate research symposium, which is dated for Tuesday, July 28th. If you would like to get a video of our previous webinars, you can email me, Latanya Brown-Robertson at L, N as in November, Brown at bowiestate.edu. First, I would like to say thank you for attending. Thank you to our Data Science and Analytics Summer Undergraduate Research Institute students for attending, as well as our faculty mentors. Thank you to the College of Business, deans, campus-wide, as well as our provost and our president. I'm going to now introduce our speaker for today. His name is Dr. Augustine Ntembe. He's an associate professor of economics at Bowie State University. He's in the Department of Accounting, Finance, and Economics. He teaches statistics and quantitative methods courses within Bowie State University. He also has a specialization in growth and development economics, and he has published in various journals, including the Journal of Economics and Finance and the Journal of Economics and Education Research. Dr. Ntembe also participated in the University System of Maryland course redesign grant to infuse and to change the redesign the principles of economics courses, which was funded by the Carnegie Foundation. He was principal investigator for the Cameroon in the United Nations research grant to complete a report on the theme of higher education and development in Africa, where he conducted research assignments in the International Capacity Building Institute for Africa. He is currently our co-principal investigator for the National Science Foundation grant to infuse data science and analytics into the undergraduate curriculum campus-wide at Bowie State University. Dr. Ntembe, along with me, Dr. Brown-Robertson, completed a research study underneath the Data Science and Undergraduate Surrey Institute last year on migration habits of single female-headed households across U.S. cities, where we utilized the American Housing Survey data set. Thank you, Dr. Ntembe, for being with us today. And I will go ahead and load up your presentation and you can get started. Okay, Dr. Ntembe, it's all yours.
Okay, Dr. Brown, thank you so much for that bio. I didn't know that it was as good as that. Today, I want to first of all greet all the mentors and the young researchers. And I'm excited welcoming them to this second session of our summer undergraduate research workshop. And this session actually will help the researchers to have a broad overview of how statistics can be used in analyzing their data. Can I? Okay. So, by the way, I would like us to, I just want to briefly talk about data analytics. What is it? Why data analytics? Actually, with the increasing availability of data, there is a need to analyze this data for our benefit. We all know that. And gathering data, either for gathering hidden insights from the data or generating reports, we need the data, we need to gather the hidden insights. We also need to generate reports that are available for decision making. What is data analytics? Actually, what is it? Actually, data analytics refers to the technique to analyze data to enhance productivity and business gain. So, I'm sorry. So it is actually a process of analyzing raw data. We collect raw data, we analyze it and find trends in the data and answer questions that support the decisions and that can be made. In short, of course, if you have an understanding of, let's say, business administration, and you also want to gather data to perform, say, exploratory analysis, you would definitely need data analytics. You should be able to have some knowledge of data analytics. You may necessarily not be a data analyst, but you could have learned it all along, like any other person is learning, just as you are learning during this summer. Who is a data analyst? Actually, a data analyst is a professional who gathers data from various sources, analyze the data, and generate reports needed for decision making. So the data may be structured data or unstructured data. I want to just differentiate between the two. Unstructured data, data is not organized in table forms. And the data is JSON-like documents. It could be messages, it could be letters, it could be just information that we collect about attributes, qualitative information, and stuff like that. We also have structured data that can be analyzed using MySQL. MySQL is actually a free, it's a free open source relational database management system, and it can be used to analyze data that is organized in tables, that is relational data. So we collect the data. We use either tools that can analyze structured data or unstructured data. We analyze the data and then we create reports. We're going to talk briefly how we can create such reports. Who is a data analyst, actually? A data analyst is someone who has some skills, some specific skills, has skills like statistics skills, like data cleaning, like exploratory data analysis skills, which is an approach to analyzing data sets to summarize their characteristics. Of course, this is often done with visual methods. We also have data visualizations. And for in more advanced situations, machine learning skills. So each of these, we're going to be looking at getting more about each of these in our workshop sessions. In the next workshop, I think we'll be talking about data cleaning and stuff, and machine learning. So the data analytics skill that we are actually going to be discussing today is statistics. We want to know exactly how helpful statistics can be in helping us go through our research for the summer. So actually, what is statistics actually? Statistics actually is a branch of mathematics that deals with data collection, organization, analysis, interpretation, and presentation. So actually, we build a model, quantifiable models to analyze the data, and then we obtain results. And these results can be presented in different forms, in the forms of reports, in the form of tables, and the form of graphs, maps, and stuff like that. What can we use statistics for? How useful is statistics? So we can use statistics to describe data. And we're going to look at using it to describe data and using statistics for discovering insights about data. That's inferential statistics. So let's just start by looking at using statistics to describe data. There are actually two key measures of the two key descriptive measures. One of them is the measures of the center, and the other one is the measures of variability. The measure of the center include the mean, the median, and the mode. And the median and the measures of variability includes the variance and the standard deviation, the range, the interquartile range, and we have we have those three. We have the range, the interquartile range, the variance, and the standard deviation. So clearly, if you look at this diagram, these drawings on your left, and you see that the first one, we have different mean. You see that the graphs are almost of the same size. They have the same size, and we expect that the mean is supposed to be the same, but that is not always the case, because the mean is a measure of location. So they do not have the same location, even though they have the same shape. So if they were having the same location, then they will have the same mean, and they will align at the same spot with the mean, the mode, and the median equal. So in the second graph here, you can see we have the same mean, but we have different standard deviations. Even though we have the same mean, the standard deviations are not the same. One of the graph is narrow, has a very low, it has a low standard deviation. The other one is broad, has a large standard deviation. Of course, that tells us that the distribution of the data is, the two data sets are not the same. One is broadly distributed and the other one is narrowly distributed. In the third graph that you see, we have different means and then we have different standard deviations. Actually, the means are not the same. The location is different. The standard deviation are also not the same. One of the graph is narrow, the other one is widely spread. So now, data visualization. It is a skill, is one of the skills that we need in data analytics. Data visualization is actually the graphical representation of information and data. It uses visual elements like charts, like graphs. It also uses maps. Data visualization tools provide an accessible way to see and understand trends, outliers, and patterns in the data. We look at this, the figure that you can see on your left. It was generated by UNESCO to measure. It was generated by UNESCO to actually measure the amount of water in different sources of food and the different types of water, like water from precipitation and other sources. And this is generated using Tableau. So actually, Tableau is very useful when presenting visualizations. Again, we may have other platforms that can help us do visualizations, not necessarily Tableau, but we have the opportunity that we had a skillful expert who help us in understanding a lot of the visualization in data using Tableau. Now, drawing a conclusion, inferential statistics. Remember, we have actually looked at descriptive statistics, and we know that descriptive statistics is mostly concerned with describing data, looking at the center, measuring the center of the data, and also the dispersion or the variability of the data. It helps in visualization, helps us in just taking a look at the data and drawing conclusion on the way the data is distributed, just like the graphs that we saw earlier. With inferential statistics, we are more concerned with applying probability to a large data set, for example, to draw a conclusion. And it allows us to measure the degree of association between variables and also perform predictions. Prediction is nothing other than predicting an outcome variable or a target variable from some explanatory variables. And an association there is simply finding the relationships between variables. And such relationships can either be positive or negative. Most often, we use scatter plots, for example, to find the degree of associations between variables. We may also have measures like the correlation coefficient, which can either be positive or negative. What can we use statistics for? So suppose we wish to find the difference or the differences in the average performance of commuter students at both state campus and those students living on campus. We want to use inferential statistics for that purpose. We may want to test the average between the two groups. We can start by building up some hypotheses, and then we use the hypothesis to test whether there's actually any difference between the two groups. So inferential statistics actually makes use of hypothesis testing. Usually, statisticians use testing to formally check whether the estimated value have any meaning. We have estimated values, and we really don't test to find out if the estimates are meaningful. We may run into making wrong conclusions because our data, our estimates may be biased or maybe inefficient in some way. We need to be able to test the hypothesis and to determine whether our estimates are meaningful. Now, what are the steps? Actually, we state the hypothesis. Usually we distinguish between the null and the alternate hypothesis. And then we formulate an analysis plan, of course. And then after that, we analyze sample data. And normally we cannot obtain data on the population. We can estimate population parameters based on sample information or sample data. So this stage actually involves the calculation and the interpretation of the test statistics as described in the analysis plan. A data analysis plan is nothing other than the roadmap on how you're going to organize and analyze your data. And of course, this should help you to achieve the main objective that you have set for your research, and also help you to look at the specific objectives that provide answer to specific questions, and that will help you in realizing the general objective of your research. Now, but coming back to the differences between descriptive versus inferential statistics, I would like to say that descriptive statistics is only concerned with the properties of the population. It measures the population like the population mean. the population standard deviation, and so forth. Inferential statistics, on the other hand, makes inferences from the sample. It uses information obtained from the sample to estimate population parameters. We're going to talk about the reliability of this process a little bit later. Descriptive statistics present data in a meaningful manner. On the other hand, inferential statistics compares and predicts the future outcomes. Descriptive statistics, with that, the outcomes are shown in the form of charts or tables and graphs. We have said this and mentioned this earlier. With inferential statistics, the outcomes are in the form of probability scores. Descriptive statistics described the known data. So you have to collect data, historical data, and data that has been collected. And then you analyze the data and create visualizations, and that can help you write stories and write reports. With inferential statistics, we try to make conclusions beyond the available data. So we collect data up to last year. We may use the data to predict what is going to happen this year or next year. And that is one of the key differences. With descriptive statistics, measures of central tendency and measures center, it deals with measures of central tendency, like the mean, the mode, the median, and the measures of spread of the data. How spread our data is by looking at the range of the data, maximum, difference between the maximum and the minimum value, the variance, the standard deviation, and other measures. Inferential statistics, on the other hand, test hypotheses and perform analysis of variance. So it uses, after estimating population parameters based on the sample, you may want to find out if the results that you have are valid, or whether they are close to the actual values. You want to test hypotheses. You can only do that using inferential statistics. So I'm just going to, like an example too. Okay, let me go to the next. So normally we can do association and, of course, association and prediction, which are some of the most things that are done with inferential statistics. Inferential statistics actually try to find the degree of association between variables, and it also carried out predictions of the outcome variable or the response variable based on a number of explanatory variables or covariates, and those variables that can significantly affect the outcome variable. So one of the things that you should also take note of is that with prediction, we do not try to extrapolate beyond the range of observed explanatory variables. So we don't want to go behind. If our data begins, let's say, from 2010, we don't want to try to go beyond sometime before 2010, because that is not going to be possible. But we can use that data to predict something that can likely happen in 2021 or 2022. That is very possible. Yeah. Now, what are the differences between means? We can use hypotheses hypothesis testing to test for the relative difference between a measure of a population parameter like the mean or the variance. For example, if we want to find whether there is a significant difference between salaries between men's athletics coaches and women's athletics coaches, we may use hypothesis testing to do that. We may use inferential statistics to do that. By using one of the tests that I'm going to show you at the, later, you can test whether there is any significant difference between the two populations, the two groups of populations. Just as you see in the normal table here, see women and then you see men. But just looking at that, you cannot tell except you conduct a test. Now, the thing is that two populations that have the same variance, and in order to conduct tests, we'll have to make like 3 assumptions. And the first assumption is that the two populations should have the same variance. And we're going to talk about variance, differences in variance, how that can affect our estimate. This assumption is actually called the assumption of homogeneity of variance. We can also have, we also assume that the population is normally distributed. We also assume that the population is normally distributed in testing our hypothesis. So then the last assumption will be that each value is sampled independently. That is, the values are independent from each other. That is very important. One of the things is that these 3 assumptions, we can violate the first 2 in a kind of mild way, and it really doesn't make a difference. But the third one, that the sample value, each value is sampled differently, should not be violated. Because if it is violated, we'll have the impression that a particular variable is causing a phenomenon to happen when it is indeed another thing that is doing it. So there's that problem. We have to be very careful when dealing with that. So I would like us to look at the relationship between predictor variables, or the differences between predictor variables and outcome variables. One of the things that you need to know is that in your research, the outcome variable, or the target variable, or the variable of interest is going to be the dependent variable, or the effect. That's what you want to measure as a researcher. It may change depending on the independent variable. So if the independent variable changes, that variable can change. If, for example, a business want to find the effect of advertising on sales, for example, and the target variable in this case is sales, or the outcome, or the dependent variable. So we want to see how advertising affects sales. And you see that changes in sales will happen if the amount of money spent on advertising is changing. Then sales are going to be changing as well. So the predictor is actually the independent variables that you're going to use in your research. That is what they call the cause, not the effect. What causes the outcome variable to change? There's a variable. We call that the predictor variable, or the explanatory variable in some terminology. And that is what, as a researcher, you can manipulate. you cannot manipulate the outcome, but you can manipulate the predictor variable in order to have an outcome. I want to talk briefly about the fact that these variables can either be continuous. The variables themselves can either be continuous or they can be categorical. They can be continuous or they can be categorical. So if they are continuous, then there are many data values within a certain interval. But if they are categorical, they can assume one of the categories. For example, if it's a binary, for example, and we are looking at the differences between male and female, then we may say female equals to 1, male equals to 0, and to describe that we have a dependent variable that is categorical. If we have a continuous variable, we know that that continuous variable should lie within a certain interval, and measures like height and weight and stuff like that, and time, they are measured as continuous variables. So actually, as I said earlier, data can be presented in the form of 2 or more categories. It could either be a rank order, data without scores. It could also have scores. For example, in a research, you may want to look at the choice of facilities. Let's take, for example, patients choosing to go to the hospital, and they may choose to go to a private clinic. They may choose to go to a national hospital. They may choose to go to a mission hospital or something. These are all categories, and each choice actually is affected by the predictors. There are actually things that motivate people to make these decisions. So the data can be represented as categories. In most cases, the form of estimation is logistic. You can estimate it as a binary logic model, a multinomial logic model, or a multinomial probability model, depending on the number of categories. Binary, when there are only 2 categories, multinomial probability and logic, when there are more than 2 categories. The dependent variable exists in more than 2 categories. With continuous variable as a scale of measurement, we have a numerical score for each data point. Of course, that data point should lie within a certain range. And there are actually uncountable values within an interval, so that it is difficult to count. For example, each time I get up in the morning and measure my weight, the measurement is different. And it's different most of the time, so that my weight is actually a continuous variable, because I will always lie within a certain range. But each time it just varies within that range. So that kind of data is continuous. Now, we can perform tests. We can estimate relationships, perform predictive analysis, find the relationship between variables. We may run regressions analysis relating 2 or more variables and obtain some results. but we have to be careful that certain assumptions are fulfilled. Otherwise, the outcome of our estimates will yield results that the outcome will either be biased or be meaningless. So we first of all start by assuming that a relationship between predictors should be represented by a straight line. And sometimes we may obtain data, like the second figure here, data that you see the data is going up and curving backward. So this type of data becomes difficult to estimate. So in order for us to have a trend, like the line that we see, we can take logarithms. We can do a kind of semi-log or log-log transformation to obtain a linear relationship that is estimable, that can be estimated. And we must also make sure that the explanatory variables are normally distributed. If they are normally distributed, then they will lie within a range. If they are normally distributed, they will lie within a range. I'll talk about that. I would like to talk about the homogeneity of the variance. The homogeneity of the variance. One of the key assumptions is that which should not be violated, is that the variance of the groups are expected to be equal. The variance do not change from sample to sample. They're supposed to be the same. They're expected to be the same. If they are the same variance, if the variance are the same, we say that we say that the property of homoscedasticity is fulfilled in this case. It actually describes a situation in which the error term, for example, is the same across all the values of the independent variables. Otherwise, if this is not the case, then it is heteroscedastic. So heteroscedasticity actually is a systematic change in the spread of the error. So that you find the error either increasing continuously or decreasing continuously over a range of the measured values. We don't need to have that kind of situation. The errors are expected to be the same. Normality. Why some of the tests of hypothesis tests that we're going to be performing do not worry about whether the data is normally distributed or not. Some of them are critically normality is critically important for some of them. With normality, we have the sampling distribution of the sample mean is a normal distribution of the residuals in the population. And this assumption is one of the key assumptions in ordinary least square regressions, in which case, with normal distribution, there is no bias in the measurement of the variable either to the left of the center or to the right of the center. Like you can see here, there's no bias in this case. There's kind of balance in the distribution of the variable around its mean and the mode and the standard deviation. Such estimates will produce ordinary least squares on our least squares that are unbiased. We also have the hypothesis, the assumption of independence. We assume that one of the key assumptions in regression is that the errors should be independent. They should be independent, and such that the observations are independent in such a way that none of the observation is able to influence the other observation. That's what independent requires. None of the observation should be able to influence or have an impact or have some compelling effect on the other observation. And in that case, there will be no evidence of serial correlation in the errors. The errors will not be serially correlated in this case. Of course, if they are serially correlated, if there's no independence among the observations, and then we'll have regression estimates that are nonsense, that are unreliable, that are meaningless. So we have to make sure that the errors are independent. Now about my data. So I'm asking the student researchers, have you created a table like this and tried to identify the kind of data that you're going to be using for your research? Is the outcome or the response variable that you're going to be dealing with, is it categorical or continuous? These are questions that you need to answer.
Do you want them to answer it in the chat?
I think so,
Linda?
yes. They should do that.
Okay, we can do a poll if you like. So let me know what's the first question you want to ask, and I'll create a poll.
Yeah, the first question is, have they identified the outcome or the independent variables that they're going to be estimating?
You identified the outcome
or the dependent variables that they'll be estimating in their research. And the next question is that if they have...
Okay, give me 1 second. Let's do this question first.
Okay, let's do that first.
Okay, yes. No. Okay, so I'm going to publish this poll right now, and I ask that you all take this poll. It says, have you identified the outcome or dependent variables for your research? So it asks that the student researchers, what about the faculty mentors? Can they take the poll as well?
Yes, they can.
Okay. Okay, we'll give you guys a couple more minutes to answer the poll.
Mm-hmm.
Or seconds. Okay, so it looks like majority of the audience today who's conducting research, 85%, have identified, or now we're going up to 87%. They have identified, now we're down to 77. Okay, I'll wait a couple more minutes.
It's not bad though.
Right. Yeah, it's pretty good. Yeah.
So the next question which I want us to pull is, if they have identified the dependent variable, that is the variable of interest that they're going to be researching on.
Have you identified?
No, if they have identified, then is it categorical or continuous?
Okay, so is there dependent variable?
Yes. Is a dependent variable categorical, that is in categories that assume different categories, or is a continuous variable like 20, 30, or within a certain range?
Okay, almost finished the question. Excuse me if my spelling is off. I'm trying to hurry up and get this out here. Okay. All right. Wait, let me put a question mark at the end, and then I will publish the poll. Okay, so is your dependent variable categorical or continuous? Okay. Most people are putting continuous right now.
That's interesting. Oh, 100%.
Yeah, I wonder, and everybody knows the difference between a categorical and independent variable. The students remember that, right?
Yeah. Let me just talk about the categories again. With a categorical, if the dependent variable is categorical, it means that it assumes different values. It is in the form of categories. It is in the form of categories. It may be male and female, for example. These are two categories. If we have only two categories, then they are binary. But we have more than two categories, then it's no longer binary. It's just categorical. So again,
right, and continuous is. Can you explain what continuous is for the student?
With continuous, the variable in question assume certain data. Unlimited number of data, amount of data within a certain range. And we can see that the data has maximum value, has the minimum value, but there are lots of data in between.
So like housing prices would be an example.
Exactly, like time, amount of time that student put in studies, like the amount of the height of the students at both State University, which is finally large because there are so many students having the same height and stuff like that.
Great. So it looks like 90% of the researchers today have a dependent variable that is continuous and not categorical.
Now, if they have that, can we know if they have also identified the predictors, or the explanatory variables, the variables that they'll be trying to use in order to explain the dependent variable?
Okay, so I have identified all of my explanatory variables.
Yes, have they identified the explanatory variables?
Okay. Okay. Okay, I'm gonna put another option in here. I'm gonna say yes, all, no, and then I'm gonna put some. Okay, here's the question. I have identified explanatory variables. Yes, I have identified all of them. No, I haven't identified any of them, or I have identified some of them.
Okay, that makes sense. So I have the final question.
Okay.
The final question is about the expected outcomes. Do you have an idea?
Okay.
Do they have an idea about what the outcome of their estimation or their research is going to be?
Okay, so maybe they should put that in the chat. So I'm going to put out here. What do you think
would be
your expected outcome would be? And you can put it in. You can put your answer in the chat. So just type, what do you think your expected outcome would be, so we can get an idea of where you want to go. So that's basically kind of what their hypothesis is, correct?
Yeah.
What are they expecting to
We'll talk briefly about hypothesis.
Okay.
Again, we'll talk about hypothesis briefly.
Okay. So
Okay.
yeah, if you could briefly, for the audience, briefly put in the chat, what do you think your expected outcome would be?
Okay.
We'd love to get some feedback from the students as well. So students, please participate. Oh, Noel said something. He said he has an idea on reading the articles. So okay. So he's getting his idea based upon his literature review on what he thinks his expected outcome would be. And I believe Noel is, you can tell me if I'm right or wrong, you're doing research on mergers and acquisitions. So he's getting an idea of that outcome as far as events or mergers and acquisitions through the reading of the literature. Anyone else have an expected outcome that they're looking to, that they think would be based upon their analysis?
Yeah. No, it has. Okay. So let me go to the next slide.
And actually, can we go back for a minute? This would be kind of cool, Dr. Ntime. Let's talk about our paper that we did on the single female-headed households.
Yes.
And everything. And just briefly, if you could kind of give them an example of that, like what we thought what we're thinking our expected outcomes would be, and what our dependent variable is, and stuff like that.
Okay. Researchers. Last year, we actually mentored a student, and it was very successful. The student was out to determine the migration habits of households that were headed by a female, single female, in the United States, in U.S. cities. The student actually initially came out with some assumption of what he expected. And then he built his model and then stated some hypotheses that he was going to test. We had a very huge data set. The data set was 65,000 observations. So the student was going to actually selected the variables that affected the decision of this cohort of households to migrate. Most of the reason was that the cost of housing was high, and so they couldn't support the cost. They had to move. He actually looked at the relationship between the decision to move and a set of values of variables that could affect that decision, like the income, like the education of the single female who was moving, and the education, the income, the prices, even the age as well. Yeah, I think these were the 4 variables that he used, because the key variable there was to look at income. How does income affect that decision? If it becomes very expensive to live, and your income is high, you could still stay. But he was going to look at the reason and some of those things that will affect that decision, other than the prices of homes, because the prices could be high, and the households decide to stay if they have good income, if they have good education that can allows them have high earning jobs and stuff like that. And these were some of the measurable things observations, variables that were included in that study. So what happened is that the student found the findings were that income was having a very significant role based on income levels, and people who had more incomes were more likely to stay than those who had less income. and that actually ties with the reality, the data. And they also found that households with more education were able to stay. I think if I'm interpreting it right, they were more likely to stay. I think because they were more likely to be employed, highly employed with high pay that could allow them, could enable them to pay the rents or the high cost of housing, and they could stay. So initially what he did was that he had a very large data set. He cleaned the data set and finally arrived at 12,000 observations. And then he used the 12,000 observation to estimate a logistic model, because the decision to either move or not to move is a categorical, the dependent variable is a categorical variable.
Mm-hmm.
When the household moved away, he gave the value of 1. When the household did not move, was a 0. And then he used this to estimate a simple logic model. And the results were startling, and they were quite impressive. So I know that a lot of you will be using very large databases, data sets, and you'll be able to clean the data. He actually cleaned with Excel, but he used Tableau to create visualizations, because he also did predictive analysis, but he was also able to create visualizations and wrote a final report that was presented at the end of the survey. And his work was highly applauded.
Great. Thank you so much.
So let me go to the next thing about my data. So we probably have talked about that. How many outcomes variables do I have? Are the outcomes categorical or continuous? We have answered that, but we haven't answered the first one, whether you have more outcomes variables or not. How many predictor variables? That is, how many explanatory variables? Are the predictor categorical or continuous? I think we have answered those questions. So the only thing we have not answered is how many of each of those variables that they have. Nearly all the students have continuous variables, so they shouldn't have more than one category. They shouldn't even have a category. So, but the next thing is how many predictors variables do they have? And they should reflect that with their mentors, and look at the number of variables that they are targeting if they want to do predictive analysis. Now, if you are doing predictive analysis and you estimate the model that you build, either to establish a relationship or to do inference on the population based on sample data that you have, you may want to test for the validity of your estimate. And there's a large number of tests that you can perform. There's a large number of tests that you can perform. With linear regressions, which a lot of you may use that, you have to make sure that you look at the fitness of your estimates. You see whether your estimates are well fitted, by looking at the correlation coefficient and the R square, which is the coefficient of determination. You may want to look at that. You may have a very high coefficient of determination, and that has little or no meaning. You may want to go further to test for the overall significance of your model. Maybe you want to use the Fisher and test and do a general test, maybe using the p-value that is estimated automatically. you can use that to test whether your estimates makes any sense or not. Now, if you don't want to do that, perhaps you are looking at two different categories, two different groups or population groups. And just like from the beginning, I said that suppose you have two populations, students who commute and students who live on campus. You want to perhaps measure the relative performance of these students on average. You want to see whether there's any significant difference or whether factors relating to where they live can have an impact on their performance. You may want to use a group of tests that are suggested on this chart. You may want to use exposure variables here. You may also want to use normal. You may also want to do your estimates, assuming that your data is normally distributed. And you may also, if you are not sure that your data is normally distributed and you assume that maybe there's some skewness in the data and you don't want to get wrong results, even though the data is not normally distributed, you can use these other groups like the sign test, the sign rank test, the Mann-Whitney. These are all non-parametric tests. The Mann-Whitney U-test, we call sign test. All these tests are easy to implement with SPSS. And even this one, the one sample t-test, two sample t-test, you can do some of these with Excel, but SPSS is, I think, is a better option. You can also estimate the chi-square, and it really doesn't matter whether the data is normally distributed or not. You can use a chi-square test. You can use logistic regression, which really doesn't matter and which doesn't really care about the form of the data. You may want to do that. If you have any questions on that, I think this is the end of the presentation, but if you would allow me to say one more thing that probably we did not look at it from the beginning. I would like to highlight here that analytics techniques, there are three different kinds of analytic techniques, data analytics techniques. We have descriptive analytics. Actually, it refers to gathering data, organizing the data, tabulating it, and performing visualization. And the goal is to summarize what has happened. We have the data. We have the data. We're not inventing. We're not creating more data. We are just describing the data that we have to summarize what has happened. Example, we include things like financial reports, like student transcripts, like public health statistics, like enrollment to different courses and stuff like that. So we can present that information as reports. Then we normally can use data visualization to do that. And the tableau that we learned last 2 weeks, was very critical for such presentation, describing your data. Very, very important. Then we have predictive analytics. This refers actually to the use of historical data that has been collected to predict actually what could happen in the future. That's a branch of inferential statistics. And the method actually requires that we build analytical models. We build the models and we build the models to establish associations between variables. And then we estimate the likelihood of a specific outcome. For example, we may want to see whether admitted students who among the admitted students into the university are likely to enroll, for example. Or maybe we want to identify customers who are likely to respond to marketing campaigns. We may use predictive analytics. We can do that by using regression, just as we discussed. You can estimate linear regression equations, models like ordinary least squares and multiple regressions, which involves several independent variables. We may also do data mining, supervised data mining, and forecasting in predictive analytics. Now, the other one is the prescriptive analytics. Prescriptive analytics here refers to using optimization and simulation to provide advice on what should we do, for example, to provide advice on what should we do. It explores several possible actions and suggests a course of action. Maybe we want to provide advice on employee scheduling, scheduling employees' work hours, for example, and supply levels to satisfy customer demand. We may want to maybe estimate linear equations. We may want to do some simulations by using optimization. We can use optimization and simulation to do stuff like that, to do prescriptive analytics. So actually, these are the three different kinds of analytics that we can deal with. So I think I have come to the end of this presentation, and I would like to take your questions if you have any.
Yes, please put your questions in the chat, and then I will order ask the Dr. Ntembe, or he can read them and answer them. Okay, so I see Dr. Zenabi has asked a question. He says, predictive analytics also supported through machine learning techniques. Very true. Okay, very true.
Thank you so much, Prof. Thank you so much.
And we'll elaborate on that next week.
Next week, yes, because he's really skillful in machine learning, and that's really what we're going to have next week. I myself, I'm going to study just like any other student. I think all of us will be there. Yes.
Okay, so another question is, can you explain what a unit of analysis is? Provide an example of a unit of analysis.
A unit of analysis in the form of an observation or what?
Okay. Do you mean a unit of analysis in the form of an observation? I believe he does mean that, like within the data set, and how you're within the prediction and analysis of it, what would be the unit of analysis? I guess an example of it would best be described through this.
Oh,
or I can ask him to elaborate a little bit more.
Okay.
Okay. Okay, yeah. He said during an analysis. So if you can you give an example within an analysis and explain what a unit of analysis is within that example of analyzing the data? within the context of analyzing the data.
Or within the context of analyzing the data?
Mm-hmm. So so let me see, Dr. Kapoor says, so if we are looking at the data to see if it supports or accepts the theory. Okay, so I'll go to Dr. Kapoor's in a minute. I believe with what Dr. Zenabi is talking about, he's talking about observations, I believe, or some of the values within the data set. Is that what you're referring to, Dr. Zenabi? You can let us know.
Okay, now, Dr. Kapoor, if you're looking at the data to see if it supports accept theory, would this be predictive? Actually, one of the things with building models is that we always want to start from some theoretical construct to develop a model that will be estimated, or except that I think that there has to be some theory. I believe that you have to build a model based on some preconceived idea, and that should be based on some theory or some explanation and things like that.
Right, or some understanding, because like you can kind of, if you connect it to like the data science methodology, that theory or that hypothesis comes from first understanding what type of questions that need to be answered within that context. Wouldn't you agree?
Yeah, yes, I do that. I I'm going back to Dr. Kapoor, right?
Yeah. So
thanks to data to see if it supports accept theory. Will this be predictive? Yes, it's going to be predictive actually, because we are trying to use data to arrive at some possible outcome based on some theory. We build a theory, we build a model based on that theory, and use data to establish the theory, which we can test. Because honestly, I don't think that you can do predictive analysis if there is no theoretical basis for doing it.
Right. Okay, so I'm going back to Dr. Zenabi's. I see Dr. Zenabi and Dr. Fox is having a discussion about the unit of analysis, and Dr. Fox actually gave some examples of the unit of analysis and how it would be based upon your research. So certain examples that he gave are people, students, customers. So if you're looking at sales data, the customers would be the unit of analysis. If you're looking at education, yeah.
Oh, okay. Like if you're looking at the students, you want to measure the relative performance of the student, you should be looking at the student. The unit of analysis should be the student. Yes, that is true.
Right.
Thank you, Dr. Fox.
So I kind of just have a simple question, but I think it's important that I want to make sure. I don't know where the students are as far as, with their statistics and their understanding with this. You mentioned a lot mean. Can you kind of explain to us the difference between a mean, a median, variance, and so forth? Just a quick explanation between us.
Yeah, I can do that very quickly. So actually, as we said before, you can describe your data by either measuring the center of the data. And to measure the center of the data, you will need to measure the mean of the data, the average of the data. You want to know the average score of the data. On average, what is the average performance of students in management 240, for example? We may have like 25 students in the class, and we add up all the scores that they obtain, and then we divide it by the number of students in the class. And we're going to get an average, and that will give us an average performance, which is like the mean score for the class. Now, the mean is always considered as the center of the observation. In most of the cases, a measure of the center. Now, and the mean, the mode actually is the observation that is the most frequent in that set of data. And the median is actually the center, the observation that is in the middle of that set of data. So if the data is normally distributed, then the mean, the mode, and the median should be the same. All of them should be at the center because they are all measures of location. Otherwise, if they are not all at the center, then the data is going to be skewed either to the left or to the right. Now, the variance actually and the standard deviation. The standard deviation is a measure of dispersion. Is a measure of the dispersion. That is how dispersed is the data from the mean. How dispersed, how spread out is the data. It measures how the data is spread out. And the variance actually measures the spread from the square of the mean. The square of the mean. We need like the mean, how spread is the data from its square, from the mean square of the mean. So these are all critical in analyzing data, because if we know that our data is narrow, within narrow margins, and then we can conclude that there is no significant difference between the distribution of the data among the different units in the data. That is, the units are close together, so the data is not highly spread. For example, if you want to look at the prices of homes in the city of Bowie, and you find out that all the homes have prices located, let's say, between 200,000 to 300,000, and that is actually a narrow spread of home prices. But if we see that there is a large spread, suppose there's a home that is, except that if they are not outliers though, there are homes that are like 50,000, and then we have homes that are like 800,000. You see that the spread is too high, and then the variance and the standard deviation will all be high.
Great. Thank you for answering that question. I'm going to give a poll. This kind of goes into the unit of analysis question, and this is for the students in their research projects. I published a poll, if you could just answer it. I'm sorry, I put the word have twice. I have identified my unit of observation or analysis. So in your research, as you're analyzing your data sets and so forth, have you all gotten to the point where you have identified your unit of observation or your analysis, and kind of going back to the examples that Dr. Atimbe and Dr. Fox were given within your data set? Let's say you're looking at school data and so forth. A unit of analysis could be students, or if let's say when we was talking about the study that we did last year on single female headed households and immigration habits, our unit of analysis was households. So it looks like most of the people have identified their unit of analysis or observations within their data set. So that's a good start to moving forward with descriptive statistics and developing their questions and hypotheses. Wouldn't you agree, Dr. Nsimbe?
I agree. Actually, if they have identify their unit or analysis is one way in into the research, because of course, except you know what you want to do, you cannot proceed with your research. And the next thing will be for them to gather their data and start looking at the data.
Right. Any other questions that you all have for Dr. Ntembe in the context of data analysis? Yeah, so another question that Dr. Fox wants to know is, have you all, after you've looked at your unit of observations and analysis, let me pull this one out here, have you identified your variables? So I'll get that poll together, Dr. Ntembe, and then if you could read Dr. Williams' question while I get that poll together, I appreciate it.
Dr. William is asking if the current statistical programs automatically plot error terms. Some of them some of them do, but you have to query it and ask for the program to plot it for you, to do it for you. Everything is possible. Most of them that I know for sure, they do it for you if you ask. So if you are, let's say, using Excel, you have to follow the commands to generate, for example, the distribution of the errors. If you want to do that, that is possible. Whatever thing you want to do, most of the packages, they have options. Even though they will not do that automatically, they have options that you can use to get what you want.
So actually kind of getting into Dr. Williams' question with the plot errors, some of these tests, like on your slide that you have here, Dr. Ntembe, with some of these tests, do they give an option for different types of graphing to show the plotting of the errors of the variables in your experience?
It depends on the software that you are using. I know that I'm used to SPSS, for example, and eViews. With eViews, you run a regression, and then you start asking eViews to give you whatever you want. Maybe you want to look at the errors, maybe you want to test for this or for test for that, or you want to see whether the estimate is stable over time and stuff. It will give it to you if you request, but you must have the idea. You must know how to do it. Otherwise, they will not just give it to you automatically. You have to query. You have to look for it by using the
right. You know, one I don't know, one cheat sheet that I always do, because I can't always remember all of these tests and whether or not something is, if my chi-square is significant and so forth, or whether or not it's accurate and so forth. So one thing that I just quickly do is, based upon the application that I have, I searched a test in a YouTube video, and then I go and watch someone interpret the results from a database, and I found it to be really quick and helpful within that process.
Yes. Actually, in most of those tests, like testing between groups and pairs and stuff, there are manuals that actually document step-by-step approach. We'll be pushing those manuals to our students if we lay hands on them. So there's a question that one of the mentors sent to ask the student researcher if they have identified their unit of observation or analysis.
Right, yeah, and I think we posed that one, and most of them said that they have identified the unit of observation. And I know the other question, what Dr. Fox was asking about identifying the variables, you actually proposed that question earlier, Dr. Ntembe, and most of them have or identified some of them or most of them.
Okay.
Right. Any other questions for Dr. Ntembe? Students, do you have any questions or Would you like Dr. Ntembe to kind of explain something in more detail regarding data analytics and analysis?
In what situation do we think we do not need to verify whether assumptions are true? In what situation?
I think what Dr. Zenabi may be getting at is when you're dealing with large data sets and big data.
Yes.
A lot of times you don't have to make certain types of assumptions because it's there. Yeah.
Yes. One of the advantage of using large data sets is that the data set is so large to the extent that the sample tends to be closer to the population distribution, in which case some of the assumptions may not be necessary. In very restricted set of data, we do have to make those assumptions because it is only with those narrow range defining stuff that we can arrive at solutions that are meaningful. But if we have a large data set, for me, I think that those assumptions are not very necessary.
Right, unless you're, I mean, one time, sometimes and Dr. Zenabi, you can kind of chime in on this as well, or we can pull you up here. You could have a discussion with us. So, well, actually, we took the speaker part over.
Yeah.
Sorry. Yeah, but with the census data, for instance, that's a large data set that we're dealing with. But sometimes if we want to kind of dig deep into a particular question, there still may be certain types of data gaps within there. And I've kind of noticed with dealing with even with administrative level data and census data that I had to kind of maybe make a proxy or certain assumptions as well.
Okay.
And so forth. So
let me talk briefly about proxy because that is critically important. You may want to study a certain characteristic of your data or of the population, and you don't have the exact variable that may capture that characteristic. You can use a proxy as long as you can explain how valid that proxy is. I think that is another way out. We know that there is no perfection in research. Research is ongoing with people coming with different suggestions. So I think that will be necessary. Sometimes you can create a new variable based on the data that you have by either combining certain variables or subtracting. That is also possible.
Right. So I see Dr. Fox, what is he saying? He said we are trying to move towards survey or longitudinal data rather than time series to avoid all of the complications of not meeting the assumptions of normal distribution. Did you want to elaborate on Dr. Fox's comment?
Yes, actually, what I would like Dr. Fox to know that the first assumption of normality is not a very, it can be sometimes we can ignore it simply by using tests that do not matter, where normality does not affect and is not a problem. Even the second one, that the variances must be constant across errors, we can also not take that very seriously. But the assumption that the errors are correlated, they are not independent, is a very serious assumption. Because if you are earning, let's say you are working and earning a very high salary, and you have spend like, let's say, 25 years working, and again, you in the course of time you have trained and maybe added to your lines of licenses and certification and stuff like that. It now becomes very difficult to tell if the high salary you are receiving is due to the certifications or it is due to the education. It is due to the longevity, the amount of time you have spent at work. So that there may be kind of conflict in trying to separate those two variables. And that's a serious problem if the observations are not independent. Becomes we may attribute the effect of something to something else.
So how would you correct for that if you're noticing that you're getting correlation?
You have to test your data to see whether the data is serially correlated. And most often, when my data is serially correlated, I have to go back and see if something is wrong with the data. I have to and start thinking of alternatives. Maybe I have to drop this variable. Maybe I have to keep it. Maybe this is the variable that is causing this. You have to look at the data again and maybe get rid of variables that are related to each other. That assumption is critical.
So Dr. Asefa, he also said that sometimes transforming the variable may help to make it normal too. So I guess what he's saying is if you transform the variable, such as finding the log and so forth, then that might eliminate that correlation.
Yes, what Dr. Asefa is saying, sometimes transforming your data can be very helpful. It can actually be very helpful because it can help you solve a lot of problems with the data. It's always advised to do that. And I think that is the right thing to do.
Right. So Dr. Ntebe, when I was doing some research on administrative level data, we were looking at tax data for Washington, D.C., and we wanted to see the effect of like earned income tax credits on whether or not people stayed or moved out of the Washington, D.C. area if lower income people received the tax credit. Mm-hmm. And so we had the addresses and we had whether or not we had the people's income levels and whether or not they received the earned income tax credits. And so we also we connected it with census level data to make certain assumptions about census block group level data because we wanted to go a really low micro level to look at the effects on certain neighborhood characteristics. Mm-hmm. But we were concerned that it was other variables in there that we weren't really kind of explaining properly this whole relationship between earned income tax credit and whether or not they moved. And so one suggestion that we did within our model is we put in a variable that controlled for fixed effects.
Okay.
And and when we put that in there, then we started getting really robust results. And with the fixed effects, and you can correct me if I'm wrong, with the variable fixed effects, it really kind of took account of other things that we might not have had access to, other observations, other data that we might not have had access to that would affect this community. And it was really simple. In Stata, it was just a simple line or simple calculation that we put within our equation and everything. So is there anything else you might want to add about, the possibility of accounting for fixed effects?
That is critically important because sometimes you have to actually control for your for your data. Sometimes you have to control if you want your data to be accurate, and if you miss those controls, you obtain estimates that are biased. You may have to do that if you initially do your estimates and you find out that there are some evidence of bias, and you want to maybe control that by adding the fixed effects variables and stuff like that. It can help reduce that bias and make the estimates efficient.
Right. That's excellent. So let's ask a question. Let's throw a question out there that we specifically want the students to ask. And if the students they don't ask, I'm going to call on you. So Dr. Ntinde, do you have a question or a comment or something that we want to direct to the students?
Yes.
And okay, so what's your question?
The first question is whether the students in their various research groups, they know whether they are going to be using they'll be using visualization, for example, or data analytics or predictive analysis. What kind of analysis are they going to be using? Have they identified that specific analysis, kind of analysis that they'll be using in their research? I know in Dr. Kapoor's group, they have determined that visualization might help in creating insights that can give some useful information about because they are looking at the effect of the virus on the creation, on the creation and survival of enterprises and stuff like that. So they may want to, they think that creating visualizations will help in making us to see exactly how the increase and decrease in the spread of the virus is affecting those enterprises, whether or new enterprises have come up, or some have gone away and stuff like that. So they're going to be using visualizations. Unlike them, I think that some other groups may be using some other types of analysis. I know that Dr. Sengupta, Sefras, and
let's see if they're in that. Let's pull on one of Dr. Sengupta or Asafa's students. What type of analysis will you all be using? So basically, what's going to have they identified what their methodology is going to be?
They need to do that.
Right. Okay. And so I see all of them there. I don't really see all of the people from my group there. I see Romar here and Justin. So Romar and Justin, if you could put I'm calling you guys. If you could put something in the chat as far as have you all gotten to the point where you're understanding if you're going to do data visualizations or a little bit of both, you're going to do some type of data analytics, or is this more of data management integrations and stuff like that? So students, go ahead, and we want to see your input as well. So go ahead and put in the chat if you identified it, and if so, what type of method and analysis, data analysis you'll be utilizing. So Dr. Williams has a question. She said, can you give me an example of related variables? So one example that I believe you gave was, what was the example that you gave, Dr. Ntinde, about those variables being related?
Yes, I said that in the case of you not being able to find an exact variable, you may want to look at variables that are close to what can help you achieve the same objective by looking at variables that are related to that in an extent. For example, if
Oh,
you're
like
looking,
oh,
yeah,
so she wants an example of a proxy variable.
like, yeah, I think so, like a proxy
Okay.
that is
Hmm.
close, is kind of close to what you are looking for.
That's interesting. Let me see if I can think of one because I know I've done it before as far as proxy variables. If anybody, if any of the faculty mentors can think of an example of like a proxy variable or related variable, put it in the chat. Can you think of one off the top of your head, Dr. Ntembe?
Oh,
Let me see. That's a good question, Dr. Williams. You got me thinking about one. I know
yeah,
I've done
I'm
it
also
before.
thinking. I'm thinking. So, for example,
Okay, so
uh-huh.
okay, go ahead.
So, for
No,
example,
go, you can go ahead.
if you want to measure, for example, you want to measure, maybe you want to measure the performance of the student, and
I was
and,
thinking about
and
students too.
in the course, and you are not able. Maybe you think that the grade that they obtain from an exam the grade are not accurate. Accurate evaluation of their performance. I may want to use something that is close to that, something that you think that can provide that information on performance that is close to grade but different from grade. Or maybe their performance on assignments, maybe their performance on discussion board, for example. I may use that as a proxy. I say, after all, students are able to perform well in a project that they have put time on it, and then that can be used to measure their performance. Then I would say, okay, I'm going to use that like a proxy for performance rather than the grades. I'm not saying
Right,
that if I have
definitely.
the grades, I'm not going to use them. I'll probably use them, but in case you don't have the grade, you have something else that is close to it.
Right. So Dr. Fox gave a good one. He says, how do you measure the number of hours spent studying in a online class? So that kind of gets into it as well as what you were
Yeah,
saying. Like, what type of proxy could you utilize to measure the number of the hours spent in online class? So for me, I actually do this a lot for my proxy for participation points in
yeah.
my online money and banking class
Mhm.
is they have this component that's similar. It's called study plan in my econ lab. So I look at how many questions that they've answered, how many times they have logged in, and so forth. And I've used that as a proxy for participation. Dr. Asefa, he gave an example of you can use industrial production as a proxy for GDP. Very good.
That's
If
right.
you
That's
if you
right. Mhm.
right, if you're working on monthly data, since GDP is quarterly data, that's yeah. So increase the frequency of that data.
Okay,
You could use that as a proxy.
that's good.
Great. Yeah. I like figuring out ways to use proxies. I guess that's my whole creative
Yeah.
side of
But,
what I
but,
do, analysis.
but you must state that is you have to state clearly that is a proxy.
Right. Yeah. Definitely. Yeah, that's true. Do we have any other questions? Are the students here? I know we're having fun as far as the faculty, but the students, are you guys here? Do y'all have any questions or
Not
need
yet.
us to kind of elaborate on anything in regards to data analytics? Hello. Hi, Noel. How are you doing? He's like, I'm listening.
Yeah, no way it's there.
Okay, great. Well, do we have any? We'll take like one more question for Dr. Ntembe. Anybody have one more question for Dr. Ntembe? So, while we are waiting for the last question, Dr. Ntembe, I want to get your opinion in the context of data analytics and statistics. If you had to choose one of the most important things that needs to be done within this whole concept of doing data analysis, what would you say probably one of the most important things that needs to be performed or taken into consideration when students kind of move forward with data analytics?
I think that because not all research has to do with predictive analytics.
Mm-hmm.
If all students are able to do descriptive analytics, and they're able to collect the data, they're able to organize the data, they're able to create charts and graphs and tables, and be able to look at the visualizations and create written reports, I think it is better than everything else. I know that inferential statistics is robust. It provides very robust results. But what if our research is not using inferential statistics? What if our research is not purely quantitative? Then we should all be able to at least do descriptive analytics. Yes, we should all,
Right.
Students should be able to do descriptive analytics. They should be able to gather data. They should be able to organize the data, put it in table form, and create visualizations, summarize the data to tell us what has happened. And that can help in decision making.
Right, and as well as offer a further path to more research questions.
Exactly.
So one interesting question that Dr. Asati had, which I think is great, how can we as professors help students embrace quantitative courses a little bit more? What are your suggestions? Because I know you have a wonderful reputation of students really enjoying your quantitative courses. So share with us some of your secret sauce to getting students into quantitative courses.
I think I have a lot to share in that regard.
Okay.
So the first thing that I walk into my quants class or stat, and I let students to keep their fear out of the class. That you are in this class, you are a scholar, you are able to do this.
Yes.
Don't even have any doubt about your capabilities because you are able to do it. And sometimes when I tell them that, oh, math is very simple, they say, you saying that because you're the professor. I say, no. No. And I always share them an experience that I had. And honestly, when I took, I took actually in the third grade, not the third grade, my second year in the middle school, third year in the middle school, my math teacher was one gentleman from Ohio. The school where I was going, I happened to have been taught by 4 Americans who were teaching on Peace Corps. His name at the time was Michael Thomas. He was a very experienced mathematics teacher, and he walked to class, gave a test, and I didn't pass well. I had like 13 out of 20 because they were grading on the scale of 20. So I went back to the dorm. I was so upset, and then I saw other students. They were like very proud. They did well. I told myself that you can do this. You can do this. Come on, you can do this. And then I started studying for the math test, the next math test. Guess what? I had 20 out of 20. A perfect score. Then when I had that 20 out of 20, I went back to the dorm and told myself that I have to stay on this. And students started coming to me. Each time they have a problem, they thought that I could solve it. So I had to work harder and harder to prevent them from knowing that I was just struggling.
Oh, wow, this is a good
And
story.
then with time, I started just loving it. It became like part of me. So I always tell students from the beginning that know that everything is possible as you are getting into this class. Everything is
Wow.
possible. Keep your fear away. Please know that quantitative courses is practice. If you don't practice, you cannot make it. But again, when you ask students to go and practice at home, they won't do it. So most of the time, you really have to create time and give them problems to practice in class. And then you just go around and look at what they're doing and do corrections or give room for open discussions.
Yeah, I love that story, and it really kind of, and I liked how you kind of encompassed it with the word of getting over fear. And whenever I see the word fear, I don't embody what the definition of fear is, but I think about the acronym of fear,
Yeah,
which is false evidence appearing real. So with students, basically what you're sharing with them is that the issues of embracing quantitative courses that they may have in that fear is just false. It's false evidence appearing real,
exactly.
and that they can do it, they can overcome it, and they can master it where people can come to them for that knowledge. So that's a wonderful story. I love that story.
Thanks.
Yep. Well, thank you guys so very much. And this has been a wonderful webinar. Thank you, Dr. Ntembe, for taking time out of your schedule to just impart knowledge upon all of us. And I look forward to seeing you all here next Thursday for Dr. Zenabi's machine learning workshop. So thank you again, Dr. Ntembe. It's greatly appreciated.
It's my pleasure. Thank you so much. And thank you, the mentors and the young researchers. Know that you have started in a milestone and you get there.
Yes, yes. And do not fear. And do not fear. You can do it. All right. Take care so much. And you all have a great afternoon.